Okay, let's get started. 2 announcements. Homework 6 is due today. Hopefully that's not a surprise to anyone. And then Project 4 will be due on Friday. Today we're going to be going back to Markov decision processes, returning to this terrifying environment where we have this pit of fire that could kill us at any moment if we take the wrong step. And we defined this as like this grid world environment. And this is a model of this world. So we've decided that we're going to model this world as a Markov decision process. And we have specific grid world characteristics that we're modeling in this problem, which say, we have some actions and we have some states, and these are what the states are. There's 3 by this many and 4 by that many, and we have certain terminal states that give us pluses and minuses of rewards, and then we had this living reward. A lot of these details are grid world specific. Not all MDPs have living rewards. Not all MDPs have gems waiting for you at the end of them. But for this grid world, that's how we define things. And in general, what we want to do in an MDP is maximize our sum of discounted rewards that we're going to receive in expectation. So this is what we mean when we formalize an MDP. We have a set of states, we have a set of actions, we have some transition function that tells us what's the probability of landing in a particular next state if I start in some state and take an action. And then we have a reward function for each of those transitions as well that says how much instantaneous reward do I accumulate along that transition. So we can model this MDP in a couple of different ways. We saw it as a graph last time. We also saw it as an expectimax tree, and here we have it as an expectimax tree, right? So we start at some maximizer node, S. We look at all the available actions. We pick some action. The hope is that that action maximizes our expected utility. That brings us to what we call a Q state, or essentially a state action pair. The green node here is a chance node. This says I get to go as a maximizer, and then the environment gets to go as a chance node. The environment decides what randomness happens after I take each action. So after I've committed to taking action A, the environment is going to do whatever the environment does after action A, and that will lead to some states with some probabilities and other states with other probabilities. Okay, just to finish the definition of an MDP, we have to have a discount factor most of the time, or we could potentially say that it's limited horizon. Sometimes we'll do that instead. But we also have to have some start state or maybe a distribution over start states. The specifics of how you want to define it are sort of up to you as the problem modeler. But if someone hands you a Markov decision process and says, okay, now it's time for you to solve this, what's the optimal policy? The techniques that we're going to develop in this lecture are going to get us to those optimal policies. Last time we started talking about policies, and we said policies are kind of like when we're playing a game. We want to have, for any state that we could find ourselves in, we want to have an action that we can execute so that we're prepared in that state. It's not enough to just have a sequence of actions anymore, because the environment could do all kinds of random stuff. Just like our opponent in a game could do all kinds of stuff that we're not expecting also. So that's why it's a policy. That's the solution. And then we talked about utilities. Those are the sum of discounted rewards. And we talked about expected utilities, or values, which are the expectation over all the stuff that can go one way or another in the environment over these chance nodes. Expectation over those of values of utilities is what we're looking for. So we want to get basically the policy that maximizes value in our MDP. And just for completeness, we talked about Q values, which would be the value of being in state S and having already committed to action A. And this would just be unrolling from there. So you would say, from that state action pair, from that Q state, what's the value of acting optimally after I take this first action that I've already committed to? Okay. Any questions on the recap? This should be familiar to folks from last time. Okay, yeah, so we talked about some of these optimal quantities, right? So we talked about V star and Q star, and these are the things that define the value of states or define the value of Q states, these state action pairs. So to define the value of a state, we had this recursive definition, and I'll put the recursive definition up in a second, where we could either define the value in terms of the next Q state and just take a max over the next Q states, or we could go further and say it's a max over an expectation of the value of the next state. And then the optimal policy is just taking the optimal action from S. This is saying, tell me which action should I take So the value is like, I ask it for, I give it a state and it tells me a number. So if I'm asking my chess oracle, like, how do I play a good game of chess? And I say, here's the state that I'm currently in, and my chess program says 5. That's not like a great answer. That doesn't really tell me how to play chess, right? Like, so this is not a super helpful chess engine. But if the chess engine says, oh yeah, you should move your rook and then it'll be checkmate, like that's a useful answer. Okay, now we're talking about actions. Now I know what to do. So today we're going to talk a little bit about wrapping up what we were discussing last time, which is how do we compute optimal values. And then we're going to move towards computing optimal policies, so figuring out what are those actions actually supposed to be. Okay, so a little bit more review from last time. We looked at V star, and here was an example with this grid world, where all of these numbers are the values of the different states in our grid. This is the pit of fire, this is the gem. And then, so when we're in these different states, each one of these corresponds to how much expected future discounted reward do I think that I'm going to get if I behave optimally for the rest of time. That's what these numbers correspond to. And so I showed this, and then I also showed this one, and I think I didn't mention this, but so now we've split each state into 4. Why would we do that? Well, because there's 4 actions. So if we're looking at Q states, Q values, we have state action pairs, and so we need one value for each state action pair. So in each of the states we had before, we're going to then mark it so that, like, there's a north, south, east, and west on this diagram. And so, like, if I just look at one of these, like, let's say I look at this one, right? So that's saying I'm in this particular state, the one that I've put a box around, and I decide to go north from that state. What's the value of doing that? Well, the value of doing that is 0.67. Okay? And so if you're wondering, like, why is this one 0.74? It's because we've decided that the optimal action is to go to the right. The optimal action is to go east. So 0.74 is the Q value of the optimal action. And 0.74 happens to be the value of the state also, because the value of the state says I'm going to act optimally. So these things have an intimate connection between them. Hopefully that makes sense. All right, so questions on this? Okay, so we have a recipe, and we were starting to get into this last time, for acting optimally in an MDP. And there are just 2 steps. Step 1, take the correct first action. Step 2 is keep executing this optimal strategy, right? It's a recursive definition. So just be optimal. Well, how do you be optimal? Take the first action correctly, and then continue being optimal. All right? So it's actually that simple. But this is the core idea behind the whole of value iteration and policy iteration. So we saw some equations for this last time. These end up being called the Bellman equations. There are a bunch of different Bellman equations. We'll take you through a variety of them today. But they're the same equations that we saw last time. When we looked at this Expectimax tree, we said, okay, well, what's the value of a state, right? The value of a state, and we can compute this as follows. We say, okay, V of S, and this will be the optimal value of S, is equal to, well, what's the first thing we have to do? We're looking at this S, and we're saying we take a maximum, because this is a maximizer node, we take a maximum over A, right? So this max becomes this max. Max over A. And what are we maximizing? We're maximizing the value of this. This next node is a chance node. So we could just say this value is Q star of SA. So we could say max A of Q star of SA. And then we would be done. But we don't know what Q star is either, right? So there's another way that we can write this. We can say Q star of SA is equal to, well, what are we doing at Q star of SA? What are we doing at this chance node? It's a chance node. That means we're taking an expectation. So an expectation, we have to sum over something. Here we're summing over all the possible next states that we could find ourselves in. So we have S prime, and we need the probability of seeing that particular S prime. So we have this probability of S prime conditioned on SA. And this is just the transition function, T of SA S prime. These two things are equal to each other. So you can think about it whichever way is more helpful to you. But those two things are the same. So I'll probably end up writing T's for the rest of the time. But just think about that as being a probability. And then what are we taking the expectation over? What goes inside of here? Well, there's the reward that we get for taking this action and seeing this transition. That's R of SA S prime. Plus, we're going to wind up in this state down here. This is our S prime, and we need the value of that S prime, which is just V star of S prime. And because that's taking us one step to get there, we have to discount by gamma. Right? So we saw this all last time. We can write Q inside of V, and we get one expression that's like V defined in terms of V. And this is this recursion that we're talking about. So if I delete all this and I make it pretty, that's what it looks like. And now we have an expression for V star in terms of V star, right? So that's our recursion right there. We have V star, we're defining it in terms of V star, just at a different state. Okay? So we're going to see a bunch of variations on this equation. This is the Bellman optimality equation for V, but we'll see a couple of different versions of this Bellman equation. And what they'll do is they'll change various pieces of it. Okay, so these are what we're calling the Bellman equations. There are other Bellman equations, but these characterize optimal values, and we're going to use this concept over and over. Okay, questions before I move on? Yes? The T component? So the T is the transition function, and so this piece here, oops, yeah, so this T is equal to the probability of S prime conditioned on A S. Right? So that's just the definition of what a transition function is in an MDP. So because we're taking an expectation, we need to get these probabilities from somewhere, and it turns out we already wrote them down. They're in our T. Okay? Yeah?
How did you get R of SAS prime?
How did you get R? So yeah, so same answer as T, really. So T and R and gamma are things that people just handed to us, and they said, here's an MDP, please solve it. What's the optimal value? Okay, so they give you a reward function. It defines a reward for each transition, each SAS prime, and they give you a transition function that says what's the probability associated with that transition. And so when they hand you these quantities, then you can go about solving the MDP. Does that answer the question? Other questions? Okay, should we try it? Should we try it on an example? Okay, let's go back to the car racing MDP. So someone says, here's your MDP, right? We're going to do car racing. This is how we're going to model it. We're going to model it with 3 states. What are the states? Cool, warm, and overheated. And there's 2 actions. What are the actions? We can go slow, or we can go fast. And then someone says, okay, solve it. And I say, okay, well, you didn't tell me the transition dynamics. You didn't tell me the rewards. So what are those? And so okay, well, here's a transition function. It says that if you're in the slow state and you take this, if you're in the cool state and you take action slow, you wind up in the cool state with probability 1. If you're in the warm state and you take the action fast, you wind up in the overheated state with probability 1. And in both of the other situations where you're warm or cool, but you take the action that switches you, then it switches you with probability 0.5. So there's different ways that we can write this down. So one is to have this sort of like graph structure, and another is that we could just write all this stuff in a table. Okay? So we could write it as like, here's a bunch of things in a table, S, A, S prime. For each one of those, we have a value of T. So if someone specifies each of these cells, then you have a definition of an MDP. Okay? So we can define it one way or we can define it the other way, kind of whichever one we like better. So this MDP, we can sort of think about it, and we can say, like, if I was going to try to act optimally in this MDP, what would I do? What would be the value of the optimal policy? How much value could I expect to get? And it might not be obvious from looking at this graph, and it might not be obvious from looking at the table, but if we look at this sort of like search tree, this Expectimax search tree, it should be a little bit clearer, like what we might need to do, right? We can compute the value of being in the cool state by just taking a max over 2 actions and then taking like an expectation over the next thing, and then taking a max over the next thing. So we talked about this last time. We said this is tricky because this search tree could be infinite, right? If we go back to this picture, there are loops in this graph, right? We could continue in this sort of loop for a long time. We could continue in this sort of loop for a long time. We could continue over here. As long as we don't go fast in the warm state, we'll never overheat, and this thing will continue forever. So this tree could be infinitely large. So the way that we're going to compute is we're going to think about depth-limited search trees, the same way that we would do in games if we had too big of a search tree. And we'll say, okay, given a depth-limited search tree, what would be the value? Well, this is essentially saying that I have time-limited value functions. It's saying, let me define vk of s to be the value of acting optimally for k steps and then ending the episode. Just like, yank the agent out of the simulation, game's over, we get to stop racing now. Like, we only act for k steps, we act optimally for those k steps, and then the game ends. Okay? So this is essentially what a depth k expectimax search would give you, and this is like, you can think about it whichever way is more helpful to you, but these are sort of equivalent versions of this. So we look at this k depth expectimax thing and we say, okay, these are like time limited values. We can compute the value v2. This is like the value of running for the rest of the tree. So this value here is the same as this value here, and it's saying run an expectimax search for 2 time steps and then stop. So let's go back to the table and see what this would look like for this example. If we look at this value function and we say, okay, v0, I'm going to act optimally for 0 steps for each of the states. Let's think about the best way to do this. Yeah, so we'll just write them side by side. So v0 of cool, v0 of warm, and then there's v0 of overheated. Okay? So what are these values? Well, it's saying I'm going to act optimally for 0 steps, and then the episode ends. So I don't even have time to accumulate a reward. These are all equal to each other, and they're equal to 0. So that was easy. Now we've computed the solution to the last layer of this tree. We're done with that last layer. Now we're going to build up the second to last layer using the computations that we just did, right? So we've computed this value because there's nothing that comes after it. It's saying 0 steps. So now we're going back to here, and now we have to come up with v1 of cool. Well, what's v1 of cool? Well, thankfully, I wrote the expression for how we get v1 from v0 down at the bottom of the slide. So all we have to do is follow the procedure here. So we take the max over the actions. That's the maximizer node. Then we have to take an expectation. This is a sum over s primes of t of s prime times, it's just right here. So let's start filling in values here, right? So what are the actions? The actions are, we could go fast or we can go slow, right? So these are the 2 actions. Let's do slow first. So what happens in the slow case? Well, we have to sum, what are we summing over? All the possible next states. Well, let's look at this picture from before. What are the possible next states if we are in the cool state and we go slow? Just cool. There's only one, okay? So let's do this. Now we have only one state to sum over, so we can actually ignore this. And the probability of seeing that is 1, okay? And what are we taking the expectation over? Well, it's R plus gamma V. So R comes from, we're going slow in the cool state, and there's only one state we can end up in, it's cool, and R comes from here. So we've already dealt with this. We have to put the 1 in there, and then we say plus gamma, which we're going to assume no discount for now, so we can ignore gamma, times V. Which V? V0, because we're looking at V1, and we're defining it in terms of V0. We have a recipe for how do we get VK from VK, or sorry, VK plus 1 from VK. So we're trying to define V1, we got to define it in terms of V0, and this is V0 of cool, because that's the next state. Okay? So we can write in the value from here. We already have that. So we just put this 0 in here, and now we have it's 1 times 1 plus 0 is 1. That's the value of taking the action slow from the cool state for one step. Right? So this is v1 of cool in the path where we take the slow action, and we've just computed the value there. We have to think about the max over all the actions. So now we have to go and say, all right, well, what was the other action we could have taken? We could have gone fast. If we go fast, we have this table here that tells us, well, 50% of the time we go to this cool state, 50% of the time we go to this warm state. So that means we're going to have to take the sum over the weighted probabilities. There's 0.5 of each case times something. And what goes in the something is the reward for each case, which is 2, 2, 2, plus, we can ignore gamma because we're assuming no discount. And then we have V1 that we want to find. And so we're looking at V0 of the two states we might end up in. Well, V0 of cool is 0, and V0 of warm is 0. So those both end up being 0. And now we're just averaging together these 2's. This equals 2. So now we can back up one layer. We've computed here. Let me switch colors. We're getting kind of busy here. So we've just done all of this. We've computed that in the slow case we get 1, in the fast case we get 2. And so our max over actions is here. The max over actions is just the max of these two values. It's 2. So this is equal to 2. So that was kind of a lot of computation, but we've now computed V1 of cool. And we did it using the values we just computed using V0s from the previous iteration. Okay? So we could do this for V warm as well. And what we would do is we would say, all right, for all these V warms, we would have to start in warm. We would take one of these two actions. Here's slow, here's fast. In the fast case, there would be some value that we'd have to look at the instantaneous reward, which is minus 10, plus the value of ending up in this overheated state. And then we would have to do the same thing with the split probabilities over the other cases. So an expectation, a max, and then the value is the max of the expectation. So we can start using this to like build up our values layer by layer. We started with V0. We said that those were just all 0. We just computed V1 of cool. We could do the same thing, and we could do this for V warm, and we would get 1. And then the value of being in the overheated state, well, we've already accumulated our minus 1 getting there, or minus 10 getting there. So the value of being in the overheated state is just 0. So we could do this one more time, and I'm just going to do it for this one. Let's try and figure out V2 of the cool state. Right? This is the max over actions. What are the two actions? Well, there's a slow, there's a fast. Right? And then each one of those is going to have different cases. The slow case is 100% probability of doing one thing, and that one thing is we get a plus 1, and then we have a sort of gamma discounted, we can ignore gamma, of getting the V cool. But which V cool? This is, since we're looking for V2, we need to ask for V1 here, and that's going to be the value here. So we already have that. We can just look at our table, put this 2 in there. So this is equal to 1 times 1 plus 2 is equal to 3. Okay? Now we do the fast case. We say fast is going to be 0.5. Why is it 0.5? Because if we're in the cool state and we take the fast action, 0.5 of the time we go to the warm state, 0.5 we go to the cool state. So first let's do the cool state. It's plus 1, and then it's plus 2. Right? So we're just reading it off of the reward function here. So plus 2, and then the value of being in the cool state, which is we just pulled this one out of the table. This one comes in here too. Okay? Plus, close that, plus 0.5 times, we have this plus 2 for going this fast direction, plus 2, plus the value of being in the warm state, because that's the one that takes us to the warm state. And the warm state we had here, I didn't compute that for you, but you can sort of go through it on your own time. And so what we'll get is it's 0.5 times 2 plus 2, that's this, plus 0.5 times 2 plus 1, that's this. And ultimately, this will give us 3.5. So now we have to go back one level to the max. This is like our max node. And so we say, well, what's bigger, 3 or 3.5? The answer is 3.5. So if I did the math right, there will be a 3.5. And then we could do the same thing for the other ones. So each time we say, okay, I want to compute the value, v2, of a particular state. I've already computed the values v1 for all the states at the previous level. I've already thought about, like, if I'm time limited by one more step, what are the values of the optimal policy? And I've computed those. Because I've pre-computed those, I can just plug them into this unrolling equation, right? So I have to compute vk plus 1 from vk, and I can do this by saving the values and then using them again. Okay, a lot of math, but hopefully that was relatively easy to follow. Questions so far? Yeah.
So you always have the previous values, right?
Yeah, so we first compute v0 for all the states, and then when we're computing v1, we might see some of those states in our expectation. And what we want to do is we want to take all the values from the previous v0 when we're trying to compute v1. Yeah. And v2, we use v1. Yeah. Other questions? Okay. Nice. So that's value iteration. Basic idea is we start with v0 of s equals 0. This means there's no time steps left, so the expected reward sum is 0. Then we have this basic recipe for computing vk plus 1, given we have vk. We just did this, and it's basically saying we have this subtree already computed. We have the values of everything there, and we can use those when we're doing this. We're just adding an extra layer on top of this expect-max tree. We can repeat this until convergence, and we have a theorem that says it's actually going to converge, which is really cool. The complexity of each iteration is it's on the order of the number of states squared times the number of actions. And if you don't see that immediately, let's look at what this update expression is doing. We have this expression for v of s. So we need one of those values for each possible s. So there's s things that we're trying to update. So we have to do this once for each s. And what are we doing at each s? Well, we're taking a max over actions. So we have to look at a things. And then what are we doing at each action? Well, we're looking at all the possible next states we could end up in. And there's s of those, right? So we have s, a, s. This is s squared a. Okay, so this is, I don't know what your expectations were, but this is like, it might be more or less than you were expecting. It's kind of interesting. It's s squared times a. So this will converge to the unique optimal values, and we'll sort of get into why that is. But this is nice. We have a recipe. We can turn the crank, and we'll get optimal values. So the Bellman equations characterize these optimal values. It says, if you want to know v star, we can define v star as whatever is true if you apply this equation to it. So we start with a v star, and if we apply this equation to it, we get the same v star out. In some sense, from math, you might have heard of this before. It's called a fixed point. It's saying that there's this expression v, which if we apply this thing to it, v comes back out. That's why it's fixed. So this is different from value iteration, which computes the optimal values. So the expression for this is saying we have some vk, and I want to get vk plus 1. How do I do that? I just apply this expression to vk. So take a look at these two expressions and see if you notice any similarities here. They're almost exactly the same equation, right? On the one equation, we have an equals sign here. And on the second equation, we have an assignment. And then the only other difference is here we have one value function and here we have the same value function, whereas here we have our next value function and here we have our previous value function. So that's the only difference. Value iteration is just basically saying, let's take the Bellman equation and use it as an update rule. So yeah, it's a sort of fixed point solution method. So if you've seen fixed point stuff before, great. If you haven't, no problem. The idea is very much the same. We're just going to compute vk plus 1 in terms of vk, and eventually we'll get to v star. Okay? So the basic idea is we're building this cake layer by layer. I think I showed this picture last time. We start with the bottom layer, and then this is basically saying anytime we want to make yeah, the analogy kind of doesn't work here because like it's saying anytime we want to make a taller cake, we can use the cake we already made as like a shortcut. So I'm not sure exactly if this picture fits, but that's like kind of the rough analogy. Okay, so we want to know if this will definitely converge. How are we going to prove to ourselves, or at least convince ourselves that this is going to converge? Well, let's think about the case where the tree has a maximum depth m, okay? If the tree has a maximum depth m, then Vm, this is the value of acting optimally for m steps, actually doesn't require like any truncation. Like we've already computed that if we have the tree. So these values are exact for the first m steps because we only have m steps. If we think about the value Vm plus 1, we might not have that if we only have our tree that goes to depth m. But we can imagine like having already computed the values in an expectimax tree of a certain depth. Let's put two trees that we've already computed side by side. Let's think about vk and vk plus 1. And now let's think about the difference between these two things. Because if we want to know if this process is going to converge, then we want to know if successive vk and vk plus 1s are getting closer together over time. So if these two things are equal to each other, it's saying we're not updating the value function. We've already converged. So we want to think about the difference between the tree at iteration k and the tree at iteration k plus 1. Okay, so this is a little different from what we were doing before, whereas before we were taking trees and we were sort of aligning them at the bottom and we were adding stuff to the top of them. Now we're aligning them at the top and we're going to add stuff to the bottom. So we're saying the value of k plus 1 is essentially doing your k steps of unrolling plus one additional step of unrolling. And all the rewards that you accumulate along those first k steps are the same in both trees, right? If I take some path down through this tree, I take some sequence of actions and the chance nodes bring me to some sequence of next states. All of the rewards that I accumulate along this trajectory are the same as the ones that I accumulate along the same trajectory in this longer tree. The only thing that's different about these two trees is down here, I have an extra round where I get to play one more step. So if there's rewards that are different in these two trees, those rewards are in this last layer. So what we can do is we can actually like extend the tree on the left down to be as long. We'll just have to fill this with zeros. And we can do that. We can say the value of the tree, if you unroll it for k steps, is the same as it would be if you unroll it for k steps and then add 0 to that. So that's no problem. But now we have two trees that are the same size and we can compare them. So we have to think about, okay, well, we know that all the stuff in here is equal to all the stuff in here. Those are equal. So the only question we still have is, well, that's unfortunately not going to be visible. We have this question, like what's inside of here? Well, let's say that we can bound our rewards. Let's say that the r's are going to be somewhere between r max and r min. Okay? So there is some maximum r, right? Some absolute value maximum of r. And this is like the biggest possible difference we could see if we're comparing against the 0 that we had over here, right? So if we're comparing these two things, and we know that this last layer is the only place they can be different, what's the most different they can be? Well, the most different they can be is if we had the maximum absolute value reward. So we can compare 0 versus max absolute value of r. And that's the biggest difference we could have. But one thing that we have to keep in mind is like there's a discount factor. The discount factor doesn't have any effect on the first time step, but it has gamma effect on the second time step. It has gamma squared effect on the third time step, and so on. Eventually we're going to get down to here and we'll have gamma to the k. Now, usually when we see things being raised to powers, our intuition is like they're getting bigger over time. But in the case of like in these MDP examples where we're using this gamma to discount future rewards, gamma is always less than or equal to 1, and usually it's less than 1. So if the discount is less than 1, gamma to the k is a lot smaller than 1. It's a lot smaller than gamma for sure. So as k increases, we're essentially taking the difference between max absolute value of r and 0, which is also just the max absolute value of r, and we're adding this term, or multiplying by this term gamma to the k, and that's saying as k increases, the difference between these two trees is going to be decaying to 0. So hopefully this should convince you that like over time, as k gets large, these two trees will only differ by that last layer, and the last layer will become increasingly inconsequential because gamma is discounting things. All right? Okay, attendance code for today. We're now going to get into policy methods. So far, we've been looking at value iteration. We've been saying, like, how can we compute optimal values in MDPs? And I said, you know, like, if I had this chess engine and I wanted to know what the best next move was, I wouldn't want it to tell me a value. I'd want it to tell me the move, the actual action that I should take. So to get there, we're going to have to start thinking about, you know, not just what's the value of the optimal policy, but what's the value of other policies? How do I know that one policy is better than another policy? If I have the optimal policy, and that's why it's got all these stars on it, right, pi star, and I want to compare that to some other policy that someone just fished out of a trash can, like, is that second policy as good as the first policy? And how do we know? How do we compare these things? So we're going to talk about evaluating policies. So policy evaluation. This is saying, here's a policy. Tell me how good it is. How much value does this policy get, please? So before we were saying we were going to like just do the optimal action. So we would be at this maximizer node and we would try and figure out what's the max over all these actions. But if someone just hands us a policy and says, here's your policy, how much value does this policy get? That's a sort of different situation. It's saying, I don't want you to take the max action anymore. I want you to take the action that this policy tells you to take. So this situation is a little different. There aren't multiple actions to consider anymore. There's just the action that the policy says. So instead of a maximizer node, we really just have a node with one output, and that output is A equals pi of s. So this is a lot different. That's actually the only difference between these two situations. So one, we're taking a max. One, we're setting the action equal to the policy action. Okay? Then we get to a chance node. The environment has a chance to respond. It does its whole like expectation thing. We get our different S primes potentially, and we're back in business. But what we would do from that next state is the same thing. Rather than taking the action that maximizes and then acting optimally after that, we're taking the policy action and then getting to S prime, and then from there we're going to keep taking the policy action. So at every step we're going to keep taking policy actions now. Because what we want to know is, what's the value? If I just follow this policy forever, how much value do I get? Okay? Everyone see the distinction here? All right. So let's think about this. How are we going to compute the values for a fixed policy? Well, right away, if there's only one action, A equals pi of s, we don't need to think about this max over a's anymore. So now we have a value for a policy, v pi of s, and whereas before we had a max over actions, we have just nothing there. This was the max. We don't have that anymore, okay? What do we have? Well, we're taking this action A because it's given to us by the policy, so we're basically already in the Q state. right? We're committing to taking this policy, so we're committing to taking this action. It's like we're starting in this green node. So we can just start with the sum over all the s primes. We take our sort of transition function from before. We multiply that by the reward for this particular transition. We add gamma times the value under the policy of the next state. So this is saying, first I compute the value of the first transition, then I compute the value of staying under this policy. And notice that there's nothing out here. There is no max action. No max. So that's the difference. So if we want to evaluate a policy, we just take the policy action, and then we don't do this maximizing step. Okay, let's try and make this pretty. So that's what it looks like. It's still recursive. We still have v pi of s defined in terms of v pi of s prime, but we just don't have this max step anymore, right? The max is missing from right here. But it works the same way, and we can even develop an algorithm to compute the value of a policy. The same way that we did for value iteration, it'll look very similar to that. So in your head, what you should be thinking about with policy evaluation is like, okay, I'm in some environment. This is maybe not the environment I hoped to find myself in, but here I am. Someone hands me a policy, and this policy says, always go to the right. For any state that you find yourself in, just jump off to the right. Good luck. And I think, I don't know, is that like a good policy? Maybe, I don't know. Let's find out, right? There's another policy I could have considered. It's like the always go straight policy. I mean, I don't know if this is gonna keep me safe either, right? There's like always that slip probability, but like, I don't know, intuitively this feels like a better policy to me than the other one, right? So how do we make that mathematical? How do we make that like precise? How do we say, what's the value of this policy? What's the value of that policy? Well, here they are. If we run this policy evaluation algorithm, which I'll show you in a minute, we get these values. And so like the value of being in this hallway and always jumping off doesn't mean that you get 0 value forever. It doesn't mean you always get -10, because there's some probability that you jump off but you slip and you happen to just land on the next square, and like maybe you sort of muddle your way through. Whereas in this case, like you're much more likely to make it there, but there's still some probability that you fall off. So neither of these is perfect. You're not always getting your 100 reward, but like you're doing okay on the right, and you're not doing so great on the left. Okay, so how do we compute these values? I just showed them to you, but like you would have to trust me that those are the right values. Like, how do we get those values? It's going to look very, very similar to what value iteration does. The only difference is that whereas before we had this max, now we're setting the action equal to pi of s. So there's no max. So we're going to turn this recursive Bellman equation into updates, just like value iteration. So we start with v0 under the policy of a particular state. We just initialize this to 0. And then we have this recursive update rule. And the only difference to the previous update rule is that now there's no max here, and that this is the value of that policy. So rather than v star k, now we're looking at v pi k. So this is what is the value of running this policy for k steps and then yanking the agent out of the simulation. All right? So we can run everything the exact same way, and this equation should look strikingly similar to the one that we just saw, except that notice that there's just no max here. Right? Any questions about how you would do this? Okay. So the efficiency now is order s squared. Why is it order s squared? Well, one s is coming from here. It's saying that there are s things that we'll need to update. If we want to compute the value function, it's going to be defined in terms of states. There are s states, so we need s updates. And what do we do in each update? Well, there's no max anymore, so there's no factor of a, but there is still this sum over all the s's. So we have another s. So there's an s here and an s here, and that's where we get this s squared. Okay, was there a question? Okay. Okay, sure, sorry. Maybe I should have waited 1 second longer. Okay, so efficiency is now S squared. Yeah, question?
So is that S prime with the summation?
It is, yeah. This one is saying, what are all the S primes that I could wind up in if I follow the policy?
So that's still counting over S again.
Yeah, all the S primes that we could end up in is potentially all the states. Depends on your transition function, but yeah, it could be as many as all the states. Yeah. Other questions? Okay. So here's another thought. Maybe I can clear off the slide a little bit and make this clearer. So without the maxes, this is like a much simpler equation. We have V, which is like a vector, or it's a system of n equations. I guess if there's n states, or if there's capital S states, it's a system of capital S equations with capital S unknowns, one value for each state. So each of the equations looks like this equation. So without the Bellman equation, without the maxes, the Bellman equation is just like a linear system. You can solve it using your favorite linear system solver. You could use MATLAB. You could use NumPy. You could do whatever you like. So this becomes a lot more tractable, and you can solve it really quickly. And we're going to use that fact to try and make value iteration go a little quicker in a minute. Okay, so first we have to talk about, now I've showed you now how to take a value function, take a policy. Someone hands you a policy, and you say, okay, what's the value of this policy? You spit out a value function. So we're going from policies to value functions. What about if we want to go in the reverse direction? What if someone hands you a value function, and you want to try and come up with the best policy for that value function? This is saying, here's a value function for, let's say it's the value function for this grid world, right? So here are the values. How can we compute the optimal policy for this value function? Let's say someone hands you V star. This is saying, if you act optimally from each of these states, here's the best you could do. Can we go from this value function to the optimal actions? How should we act based on this value function? So it turns out we can use the Bellman equation again. Let's write down the Bellman equation again, right? So we have this max over actions. We have this sum over states of all the transition probabilities, SA, S primes. And then what are we adding up? Well, it's the reward for that transition plus gamma times V star of S prime. But remember the sort of chess oracle example? Like this thing is going to spit out just a number. And what do we want? We want it to spit out an action. So is there any way that we can quickly just change this? Because like what we want is the value, we want the action that maximizes this expression. So in math, there's a name for that, and it's actually just called the argmax. It's like the argument that maximizes this expression. And so if you just put that arg in front, you take this argmax instead, this will give you an action. This is saying, what's the action that leads to the best value? So when we were looking at like the car racing example, we sort of like, we said first there was the slow action and then there was the fast action. For each one of those, we would compute the value associated with taking that action. And then when we would come back, we'd say, okay, whichever the one had the higher value, we take that value. Now what we're saying is whichever one had the higher value, slow versus fast, we take that action, and that's the thing that goes out, right? So then what we can say is that pi star of S is equal to the argmax over this expression. So all we've done is we took our same Bellman equation from before, and now it's not recursive. We don't have V star in terms of V star. We're saying we can define pi star in terms of V star if we just replace the max with an argmax. Very simple change. Okay? So let me make this pretty. So So we're doing just a little expectimax search, one step of it, and in that first step we're thinking about all the actions that we might choose, and then we do v star after that, just so that we can see, well, which one leads to the best value. So this is called policy extraction. It's getting us the policy that is implied by the values. What is the policy that you would need to take in order to get these values? Here's another way of looking at this. Imagine someone gives you the q values instead of the v values, right? So now they've given you, in this case, 4 times as many numbers. So this is more information. Maybe it means we will get to do less compute. All right, so what should we do here? Well, let's say that I'm in this state, right? I can even draw that in a color that's readable. Oh, apparently I can't. All right, here's blue. So imagine we're in this state. These are the q values. What's a q value? A q value says, first I'm going to take this action, then I'm going to act optimally after that. First I'm going to commit to doing just this action, no takebacks. Then after that action's done, what's the maximum value I can get thereafter? So if we want to act optimally, and we have these q values, these are associated with going north, south, east, and west. So which one of them looks the best? We got a 0.76 going up, we got a 0.70 going down, we got a 0.89 going west, and a minus 0.62 going east. If this were me, I mean, I would pick going west. That's this one. So like, this one seems to me to be the best q value of all those 4 q values. So if this is saying pick the action that maximizes the first action reward plus the remaining value, we can write that on the slide as like pi star is just the argmax over the q values. So if I'm in this state, remember, like there's some probability that I slip if I try and go up or if I try and go down. If I move into the wall, I can't go backwards. So it's the safe thing to do. That's why I'm getting 0.9 here. So like, how should we act? Well, maybe we should just like try and maximize the q values. So it's super trivial to decide if you have q star, how you should construct pi star. You just take the argmax over q values. Does everybody see that? Okay. So very important lesson here. Actions are easier to select from q values than from values. All right. So now we have a way of going from policies to values. That's policy evaluation. It's saying how good is this policy. And we have a way of going from value functions to policies. It's saying here's a value function. What should I do with it? And so you might be thinking ahead and saying like, hey, we could actually maybe use these together in some way. And this is what's going to be called policy iteration. So with policy iteration, we're going to start with some policy. It might not be the optimal policy, but it's some behavior, some, bad policy that we fished out of the garbage, and we want to slowly improve that policy so that it becomes better and better over time. So why would we want to do that? Well, we already talked about this. With value iteration, we have this max over actions, and this costs us a. This is like the a in the s squared times a. So it's slow because we have this a term. And when we were looking at policy evaluation, there was no a term because we know the policy. We're just going to take the action it tells us. Okay. So the other thing is, it will turn out that the argmax at each state rarely changes. So if we look at this grid world example and we watch what happens as we go through value iteration, at k equals 0, there's just zeros everywhere. At k equals 1, it's sort of boring. But then we know gradually as we increase k, the value starts propagating through the rest of the grid, and so it sort of moves like this. But like, let's watch what's happening here. Watch what happens to this action and this action. So I didn't tell you what these arrows were before, but the arrows are which action maximizes the Q values. So this is like, what's the greedy action? So if we take one time step, notice that these two actions, they don't change, right? These actions, take a look at these. Okay, so now we're looking at these two actions. They don't change, right? So you might notice in the middle here, we have this action. It's changing, right? So from 3 to 4, that action is changing. So what happens next? All right, so we set this one to here, and it stays the same, and it stays the same, and then it stays the same, and then it stays the same. So like over the course of several steps, that action isn't changing at all, right? Once it moves, it doesn't move again. And then it changes at time step 10. So it moves from here to here. But like most of these arrows are not changing most of the time. So if we're always looking at all the actions, it's like we're always evaluating all of the policies rather than only the policy that we're currently looking at. So if we go back to this sort of slide, this is saying problem 2 is that this argmax, when we're doing value iteration, the argmax rarely changes. So why are we taking the argmax? Why are we looking at all the actions? We could just be looking at the best action, and then we just have to make sure that it's the best action later. And the other thing is that the policy often converges long before the values. So if we get to k equals 10 and we see that the policy has changed to this, it stays the same at k equals 11, but it also stays the same at k equals 12, and it stays the same at k equals 100. Like, it doesn't change for the next 100 steps. It's like the policy is already converged long before the values have converged. So like the values may not converge for 100 steps, the policy converged after 12. So if we just care about actions, we might not need to do all of this value iteration stuff. We might have a better policy long before the values have converged. So these are all the problems with value iteration. And now we would like to try to develop a method that uses what we've already built to do this more efficiently. So this is called policy iteration. It's an alternative approach for computing optimal values. And it has 2 steps. The first step is policy evaluation. So we start with some arbitrary policy. Could be some arbitrary policy we just fished out of the garbage. We calculate the utilities for that fixed policy. We know how to do this. Policy evaluation. Someone hands us a policy. We say, okay, the value of that policy is v pi. That's step 1. Step 2 is policy improvement. It says, okay, that policy was fixed. I know what its value is, but now I want to see, is that policy as good as we could do for those values? So now we say, here's a value function. Earlier we said, this is like sort of policy extraction. You can kind of think of it like policy extraction takes a value function like v star and says, what are the optimal actions? But that doesn't have to be v star. It could be any v. It could be any value function. So we say, all right, here's a value function. How do I act optimally with respect to that value function? That's what policy improvement is. And it will end up looking exactly the same as what we saw before. So this one here says I have some policy pi, and I want to get some value function v pi. This next step says I have some value function v pi, and I want to be greedy with respect to that value function and get like a pi plus, something that's slightly better than pi. And then we just repeat these 2 steps. At some point, the policy improvement will give us pi plus equal to pi, and then we can stop. So if this process doesn't change the policy, we're done. We can just return that policy, and now we haven't even needed to wait for the value function to converge. We can stop early. Okay, this is called policy iteration. It's still optimal, and it can actually converge much faster. Okay, so for a current fixed policy, we find the values with policy evaluation, and then we iterate until the values converge. So this is the same policy evaluation equation we had before. This is saying fixed policy. For a fixed current policy, what does that mean? It means that there is no max here, right? It's saying we have a fixed policy. We want to get v pi k plus 1 in terms of v pi of k. we're only taking the action that the policy tells us to take. This is like the evaluation version of this Bellman equation. This is the update that will get us closer to the value of this policy. Okay? Then, once we have that, we have to do one step of look ahead to see what's the best we could do if that was the value function. So we have to say, all right, we have some initial policy pi I, we have its value function, and we want to run through this argmax. This is essentially the policy extraction step we saw before, but here we've replaced, this was v star before, but now we've replaced that with v pi of whatever our pi I policy was. And now we're just pulling out what's the one step look ahead best action I can choose if I was trying to maximize this value function. So this is a very similar idea to what we saw before, where this was just v star, and now we're just saying extract the best policy for this value function, regardless of whether this value function is optimal. Both this and value iteration, so now policy iteration and value iteration, they'll compute the same thing. And you might be thinking like, hey, these feel like very similar. I actually don't know which one is which. I'm confused between the differences between value iteration and policy iteration, policy evaluation and policy extraction. What are all these things? So in value iteration, every iteration updates both the values and implicitly also updates the policy, because we have this argmax over A's. We don't track the policy explicitly, but we're taking this maximum over actions, and that sort of amounts to recomputing it at every time step. In policy iteration, we're going to say, okay, I'm going to stop doing this max over actions thing. It's too expensive. I'm just going to take my policy. I'm going to figure out what the value of that policy is. And once I'm sure that's its value, that's when I'm going to update my policy to be greedy with respect to that value function. So we only compute a new policy after we've converged the value function. And the new policy will be better, or it's not going to change. If it doesn't change, we're done. We don't have to keep iterating here. If you've seen this concept before, it's called dynamic programming. It's saying that we're going to basically cache the results of our previous computations so that we can run future computations faster. So you might have seen this in like algorithms classes, or you might have seen this in some other CS classes. Like dynamic programming is like a useful tool. These both constitute dynamic programming solutions, and it's just a generally useful concept. Like, why would we do more work than we have to do if we can just cache the work that we've already done? Okay, so if you want to compute optimal values, you have two options. One is value iteration. That's the one we started last time when we began this class with it. And that's the one where we say we want to write v star of s in terms of some stuff that's a function of v star of s prime. That's value iteration. And the stuff involves a max over actions and a sum over next states. Let me try and make that slightly cleaner. Right. It's a max over actions, a sum over next states. Okay? So policy iteration has two steps. It's saying v pi is equal to ignore the max. So it's a sum over next states times v. There's a v pi of s prime in there. So there's also other stuff. There's like rewards. But like that's essentially the change, right? So we're saying v pi, and we're going in terms of v pi, and we don't have an argmax or max or anything. If we want to compute values for a particular policy, that's this policy evaluation. So that's the first step of policy iteration. So this is just policy evaluation. The next step is policy extraction, which says I want the argmax over A of, it could either be Q star of SA, or it could be like we take this sum over S primes of some expression that has a V in it. And that V could be either V star if we're trying to extract the optimal policy, or it could be like a V pi if we're doing policy iteration. So there's a lot of different pieces here, and you might be thinking like, oh my gosh, you just showed me a bunch of stuff. All of that stuff looks the same. how am I ever going to remember the differences between these things? If you think that these all look the same, you're right. They do. They are the same thing with these tiny little tweaks, right? There's just whether you use a max or you use an argmax. Well, why would you use an argmax instead of a max? It's because you want actions coming out instead of numbers coming out. So the thing to remember here is like, why would we do one of these trade-offs? If we want an argmax, it's because we want actions. If we do a max, it's because we want values. If we have v star, it's because we want optimal values. If we have v pi, it's because we want policy values. So the differences between these are very subtle, but they all have sort of intuitive interpretations. So they do all look the same, but they all use this sort of like common language. And so you really only have to learn the one thing, and then all of the modifications to it, you can kind of think through like, oh yeah, do I want a max here or do I want like an argmax here? And one will give you a value and one will give you a policy. Okay? Questions about the differences between these things? This can be quite challenging to keep these all straight. Okay. I'll take your stunned silence as everything makes total sense. So one thing that I want to mention about MDPs is that planning requires a model. Okay, so this is like the world, and this is our model of the world. These two things are not the same thing. We've chosen to take this world and call it an MDP. MDPs are made up. The world is real. So we made this up and we said, this is our problem model, and we're going to solve this and hope that it helps us to do that. So try not to get these two things confused in your heads, because like this is a pretty central concept. We're modeling the world. We want to make good decisions in the world, but we're using our model to figure out what we think those decisions should be. If our model is bad, it means that we're not going to be able to make good decisions in the world. We might be able to make great decisions in our model, but they won't mean anything if we have a bad model. So what we've shown you so far is, here's the world that you want to make decisions in. Someone hands you this model, how do you solve it? Or someone hands you this model, how do you solve it? You want to be racing that car, but we only have tools for solving these kinds of models so far. Right? And if we go back even further, someone handed you this Pac-Man problem, and we said, okay, our model is going to be minimax search. Or, someone handed you this problem, and we said, okay, our model is going to be a graph. It's just going to be a search for the shortest path or something like that. Right? So in each of these cases, we start with a world, and then someone hands us a model of that world, and we have to go and do optimal planning with that model. This is the model that we've been talking about lately, this Markov decision process. And so it's saying that if someone hands me a set of states, a set of actions, a transition function that describes the probabilities of those transitions, and a reward function that describes the rewards for those transitions, and if they hand me a discount factor and they tell me what state I'm starting in, I'm off to the races. I can run value iteration, I can run policy iteration, I can do all that stuff. But where does this come from? Like, where does this model come from? How do I figure out what these quantities are just by interacting with the world? So we won't have time to get into that this class, but we can kind of gesture at it, and then we're going to get into this a little bit more in the next unit with machine learning. So this is like, how do we build up a model of the world from data when all we have is like raw experiences? How do we go from this kind of world to that kind of model, or any of these examples? Okay, so how do we learn these kinds of quantities? And to just kind of prime you for this a little bit, we will take a decision-making example involving one-arm bandits. Has anyone ever played a slot machine before? I don't think that I actually have. So the way it works is you pull the arm, and money either doesn't come out or it does come out. Usually it doesn't come out. In this example, we have one that actually it just always pays out $1. That's kind of a nice slot machine. And in this one, we have one that does double or nothing. So with some probability, it pays out $2, and with some probability, it pays out $0. Now, depending on how frequently it pays out $2, that might be a better bet. But if all you see are these two one-armed bandits, you're this agent, you're like, which one am I supposed to choose? So we could model the scenario as an MDP. Maybe someone hands us an MDP and they say, okay, here's the MDP for this double bandit scenario. The MDP looks like this. There are two states. Either you just won or you just lost, and you want to choose what your next pull is going to be. You can choose the blue arm or you can choose the red arm. If you choose the blue arm, you always get $1, whether you just lost or you just won. You could argue that you don't even need states in this case, but the way that we've defined MDPs, you sort of need to have two states. But so the blue arm always gets you $1, and it always wins. So that's nice. And then the red arm sometimes gets you $1. Sometimes gets you $2, and sometimes gets you 0. So let's see what color I'm on. Yeah, we'll use purple. Okay, so purple. So sometimes it gets you $2, and the probability of that happening is this probability. So 75% of the time you get $2, 25% of the time you get $0. And those probabilities are sort of independent of which state you started in. Okay? So let's ignore discounting for the sake of this example, and let's just say that we have 100 pulls, right? We have 100 time steps to try and extract as much money from these two bandits as possible. So how would we do that? Yeah. Just pull the red bandit, right? Why is that? Because yeah, so if we pull the red bandit 100 times, we're expected to get $150, right? So we can calculate these values, and we can calculate them for blue. Well, blue just gives us $1 each time. That's $100. But red, 0.75, we get $2. So if we run it 200 times, that should give us $150. So if we're trying to decide which arm to pull, we just solve the MDP, and then we pull that arm as many times as we can. Okay, so we could do that, and maybe we've just solved our MDP. We take this policy with us to the casino, and we see these two, and we know what to do because we've already calculated it in advance. So we're just going to pull the red arm. So let's pull the red arm. We get $2. Let's keep pulling it. We get $2. Okay, pull it again. $0. $2. $2. 2. 0. 0. 0. Okay, we pulled it 10 times. How much money did we get? We got $12. I thought we were supposed to get sort of like $15. Why didn't we get $15? Yeah. There could be an error between the model and the real world. What else might have happened? Why can't we get $15? Yeah. 15 is not a multiple of 2. So if we pull it 10 times, there's no way we could ever see $15, but that's the expected value. So there's another problem here, which is that we're sampling, right? We saw sampling with Bayes nets, and we saw sampling with all that. So like, this is saying that the sample is not equal to the expectation because we didn't have enough samples, maybe, right? Maybe if we had more samples, if we ran this for 200 times or 1,000 times or 10 million times, we would start to see numbers that are closer to the expectation. Okay, but the thought came up, maybe our model is wrong, right? Maybe we aren't actually so sure about what these probabilities are. Let's try thinking about planning with an unknown model, right? So let's say that the blue arm still gets you $1 every time, but now we don't know what the probabilities are for the red arm. Okay, well, we can't solve the MDP, so what is there left to do? Well, let's just play, all right? Do we want to pull the red arm or the blue arm? Red arm? Blue arm? Okay, look like more people like the red arm, so we'll do the red arm. Okay, $0. Now which arm? Just shout it out. Red, okay, a couple reds. We'll just keep pulling the red arm. Okay, 0 again. What do we think? Okay, so some people are already abandoning ship, and some people are like, no, red's going to pay out. Let's try it again. All right, let's see if red pays out. 0. Okay, is anyone jumping ship? Does anyone still think red? I still hear a couple reds. All right, let's keep... Okay, now we got a 2 on red. All right, so do the red people feel like they're vindicated? Like, should we keep pulling red, or should we keep pulling blue, or like, what should we do? Blue? Anyone think red? Okay, we got a couple reds. Let's just pull red like a few more times. Let's say that we get red 2 out of 10 times, right? We get $4 out of a possible $20. All right, now that we've done it 10 times, who still wants to pull red? Okay, those people might want to come and talk to me after class. The rest of us probably are doing well. Yeah, so what just happened? Like, we have these 2 arms. We didn't know what the probabilities were, but then we like got some data, we gathered some data, and then we had a much better idea of what the probabilities were, right? So at some point, we realized that probably blue is the right bandit to be pulling. So technically this wasn't planning, this was actually learning. So we are building the model and planning in it at the same time. This is technically reinforcement learning. We'll get to this in like a couple of lectures after spring break. There was an MDP, I showed it to you, but we didn't know what the probabilities were, so we couldn't solve it with just computation. We had to actually act and figure out what those probabilities are from experiences. And there are some important ideas in machine learning that we'll see soon, starting next class. One is that we're sampling because of chance. We have to try things repeatedly and get a better estimate over time. Second is parameter estimation. We want to know what's the most likely explanation of the data that we saw. And so that likely explanation is, oh, red's just not that good. But the more data we have, the better our estimates. So we're going to have these concepts in our minds, and we're going to try and use those to build better models of the world next time. Okay? Thanks, everybody.